Okay, now let's look at the Boltzmann learning rule. So this learning rule is rooted from statistical mechanics. So the Boltzmann machine is a neural network, which is based on the Boltzmann learning. It's actually related to the Hopfield network. We may look at the restricted Boltzmann machine later. So in this case, in the case of the Boltzmann machine, the neurons constitute a recurrent structure. So as you can see on the next slide here, so you have a recurrent structure where you have visible neurons and then hidden neurons, K of the visible neurons, L of the hidden neurons, and these neurons are connected to each other, so you have full connection between all the visible neurons and the hidden neurons, but also a connection between all the visible neurons with the other visible neurons, and also all the hidden neurons with all the other hidden neurons. So you have, and this connection is bidirectional, as you can see here. Yeah, except there is no connection between a neuron and itself. So there is no self connection. There are stochastic neurons as opposed to the Hopfield network where they're deterministic. In the case of the Boltzmann machine, they're stochastic neurons, meaning that they, we're going to explain what I mean by stochastic neuron, but they operate first in a binary manner. They're either on and off, or +1 and -1. So the state of each neuron is either +1 and -1. As I said, there are visible and hidden neurons, and they're stochastic, meaning that they are in a certain state, +1 or -1, with a certain probability. And then you can look at the, so this machine, this Boltzmann machine, has an energy function which is given by this E, which is -half of this double sum, the weights, xi, xk, xj. So if you take neuron xj, one of these neurons, either hidden or visible, and another neuron xk, so you look at the weight between them, wkj, and you sum. So if you take, this is your neuron k, this is your neuron j, so they're both in a certain state, +1 or -1, and then there is a weight between them. There is this weight between them. So this is the first term, and then you take the product of the weight. So you take another neuron, you look at the weights and the state of the other neuron, and then that's that term. And then you take another neuron. So you consider all the combination of all the neurons in the network, and you compute this energy function here. And then J is different than K, means that there is no self-feedback, as I mentioned here, that you don't have any self-feedback. Okay. So how does the Boltzmann machine operate? So you choose a neuron at random K. So you go to your machine, you pick any neuron at random, and then you flip the state of the neuron from state xk to state -k. So if it was in state +1, you flip it to -1. So this is a random perturbation with a probability. So the probability of going from state xk to -xk is given by 1/1 plus exponential minus delta ek t. So this delta ekt is the energy change of the machine resulting from such a flip. So flip from state xk to state -k. And if this rule is applied repeatedly, the machine reaches thermal equilibrium. Note that this T here is a pseudo temperature. So this is what you want to achieve, a thermal equilibrium. But you operate in two modes of operation. The first one is the clamped mode of operation, where the visible neurons are clamped onto specific states determined by the environment, i.e. you have a training set. So you take these visible neurons and you clamp them to a certain state. So this one +1, -1, +1, and so on, based on your training set. So this is the first mode of operation. And then you can perform training under this clamped condition. You can also, as we can see, or we will see next, you will also have another mode of operation, which is the free running condition or mode of operation, where all the neurons, visible and hidden, are allowed to operate freely. So you don't have an input from the environment. So you don't have any input from the environment, and then you operate, you perform this flipping, you flip the state, and until you reach the equilibrium. So such a network can be used for pattern completion. It can be also used for actually classification and regression, but the main or the fundamental starting point of the application is the pattern completion. So in this case, the goal of the Boltzmann machine is to maximize the likelihood function using the gradient descent or the log of the likelihood function, so you want to, this is the likelihood is the product, the product of the probability that your neuron, your visible neuron is at a certain state. So X alpha represents the state of the visible neuron, as opposed to X beta, which represents the state of the hidden neuron. But we don't have that in the likelihood function. Here, the gamma, this set here denotes the set of training examples drawn from a PDF of interest. Okay, so the set of the synaptic weights. So once you perform your learning, you reach your equilibrium and so on. So the set of synaptic weights that are obtained is called a model of the environment, meaning that you model your input if it leads the same probability distribution of the states of the visible units. So the learning rule or Boltzmann learning rule in this case, which was suggested in 1986, you modify your weights, the weight between a node K and a node J, by using this formula where you have a learning rate, eta, and then you have rho plus and rho minus. And these values, these rho plus and rho minus, range in, they have a range, they range in value from -1 to 1. So what is this rho plus? The rho plus denotes the correlation. This is the correlation between the states of neuron J and neuron K, with the network being in a clamped condition. So this is the product of the states multiplied by the probability that you are in a clamped condition, so that your neuron takes a certain, your visible neuron is in a certain state X alpha. While rho minus is the correlation between the states of neuron XJ, J and K with the neuron, with the network performing or running in free running condition. So you don't have this condition X alpha equal lowercase x alpha. So this is, don't panic, this is just an overview of the Boltzmann learning rule. We may have the chance to cover in detail the Boltzmann machine. It would have been great to cover the Hopfield network, and most probably we'll cover the restricted Boltzmann machine. So this is the end of our learning rules. Now, just talking about network complexity. So there is, for a while, there was no formal method which allows you to determine the network architecture. For example, the number of layers in a feed-forward network, the number of nodes in each layer, until recently with contribution in meta-learning. And that's because this lecture is about learning, so I'm talking about the meta-learning. In the next lectures, we'll focus on specific networks. But just to, I would like to recommend this paper, Meta-Learning in Neural Networks, a survey. So this has been proposed recently. So in this case, you can learn a number of things. You can learn the architecture even of the network. You can learn the hyperparameters. That's what I call the number of layers, you can learn number of layers, number of nodes per layer. You can learn a number of other things, as you can see here, denoted by the meta representation. And the methods which are used are the meta optimizers, they call them. So you can have a gradient approach, a reinforcement learning approach, or evolution-based approach. And that fits in the model agnostic meta-learning, for example, where you have a hierarchical optimization function that you need to solve. There are a number of applications for few shot learning. We will cover or talk about some of these later. But if you are interested in this area, so you can notice that so if you have a certain meta representation to solve, for example, if you want to learn your hyperparameters, you can see that there are a large number of techniques which are gradient-based techniques to solve these meta representation. There are fewer using reinforcement learning, but there are very few using evolution algorithms. So if you're good at evolution algorithms or with evolution algorithms, you may be interested to contribute here. Another paper that I would recommend is on this one here, which has been also published in July. It's in Archive in July 2020 on the hyperparameter optimization for machine learning algorithm. So it's also a survey on this topic. So this is just to solve this problem here, the optimization of the hyperparameters, meaning finding the number of layers and number of nodes per layer and so on. Some suggested reading, Haken, Fawcett, Lipman. This is a very old paper, but it's actually very good. It summarizes very well the area of neural networks. And also this is a very good paper by Whitrow. Thank you.